Friday have been inputted. I still have some people that need to take that, so I'm not going to give those back to you until tomorrow. I plan on having another in-class assessment at some point this week. And the plan is next week, towards the latter part of it, Thursday and Friday, to have our first test. Okay, so that'll be something that we're moving towards. When we do a test, obviously, I like to go back through the quizzes and look at questions that we've struggled on and put those on the test. Okay, it does make sense because then it targets whether you are doing the things necessary. When you see the feedback that you got and the issues that you had on questions on quizzes, are you taking the steps necessary to better yourself in those areas? Okay. The start of piecewise functions, okay, is actually going to take us to a quick, it's not extremely quick, but a discussion of previous functions that we've already dealt with. We need to remind ourselves of these and a few more because it will just make the process of graphing what we call a piecewise function a lot simpler, okay, and more efficient. The first thing is we've got some linear functions here. So linear functions come in two varieties. You can have what we call a constant function, okay, and the reason that's called a constant, let's say if this b value is, say, at 3, is every y value on that line then going to be 3? So the y values are constant. Does that make sense? Okay, there's no change in your y values. Here, there's change in your y values, right? Okay, so that's we call this a, mx plus b. Sometimes we refer to it as ax plus b. But that's kind of your general, generic version of any other line that is non-constant. Now, you could put a 0 in there for m and get your constant, right? Okay. But those are the two types of lines that we're going to see. So hopefully that's not something we have to talk too much about. These types of functions, okay, so I like to refer to these, and a lot of other math people will call these parent functions. Okay, parent functions. And the reason we call them parent functions is because they are kind of the most simplistic version of, let's say, a parabola. Does that make sense? X squared is the most simplistic version of that. And then we can start adding terms to that have a certain relationship. If I'm going to add terms to x squared, then I need to have, or I can only use x terms that have a power of 1 and constants. That's the only thing I can add or subtract those things. Okay. If I go to x cubed, then I can only add or subtract x squareds, x to the first, and constants. Right? Does that make sense? So we have to maintain that polynomial structure. But we call these parent functions are the most simplistic versions of what we call a family of graphs. Okay, I can take that x squared and I can move it left, I can move it up, I can move it down, right. Okay, I can flip it along the x-axis or the y-axis. I can make it change a lot, right? But no matter how I make it change, it's still a parabola. Okay, and it still has a parent function of x squared. If I understand the parent function, it makes piecewise functions so much easier, and it makes transformations, the moving of left, right, up, down, reflecting, stretching, shrinking, compressing, that kind of stuff. It makes that process, which we'll get to later this week, a much easier process. Okay. So when we look at the power functions, what I want you guys to do is commit to memory a series of points for all of these. I don't know why the Zoom on this is messed up today for some reason. All right. So I want you to commit to memory. 0, 0, 1, 1, 2, 4, negative 1, 1, negative 2, 4. And hopefully that's a series of 5 points that you already knew, okay, because you've worked on these for 3 years now. It's critical, though, to be able to do that. It's critical to, once I see x squared, those 5 points kind of jump to the picture, okay? They're going to be what we use in our transformations to make that process a little bit easier later on. And again, remember, all I did to get those was I chose integer x's, plugged those in, and got my y values back. Okay. Some critical points on x cubed are 0, 0, 1, 1, 2, 8, negative 1, negative 1, negative 2, negative 8. So as we have these discussions about graphs and plotting new graphs, new functions, like these piecewise functions that we're going to talk about here in a little bit, I'm going to quickly refer to, a cubic in those 5 points. Okay, so I want you guys to know, how am I getting those, where are those coming from? X to the fourth, okay, is very similar to x squared, except for between 0 and 1, it gets a lot flatter down here at the bottom. Okay, so maybe that's, or I guess negative 1 to 1. It's because we're taking like let's say I took an x value of 1/2 and I raise it to the fourth power. That becomes 1 over 16, right? Where if I took over here the x value of 1/2 and squared that, it's 1 over 4. You see how 1 over 16 is a much smaller value than 1 over 4? So when we're between negative 1 and 1, that x to the fourth kind of bottoms out. Okay, it's a lot flatter down here because of the idea of squaring a denominator, or I guess in this case raising to the fourth power a denominator. Is going to make that ultimate product a lot smaller, a lot quicker. But some key points on here: 0, 0, 1, 1. If I take 2 and raise it to the fourth, I get 16. And then negative 1, 1, negative 2, 16. Okay. I'll show you x to the fifth here. 0, 0, 1, 1 again. And now a point that I probably don't want to graph, but 2, 32. Negative 1, negative 1. Negative 2, negative 32. But the idea here, think about looking at just the x squared. That point, that point, that point. Are those on x to the fourth as well? Does that make sense? Okay. If I look at the cubics, negative 1, terrible. There we go, negative 1. Negative 1, negative 1, 0, 0, 1, 1. Are those also on your, we call it a quintic or a fifth degree? Are those 3 points, negative 1, 0, 0, 1, 1, still on that one? Okay. So there's some, and it's based on whether it's an even power or an odd power, but there are some shared ordered pairs because of the nature of how we deal with raising 1 to a power. Okay. And if you can remember those relationships, it's going to make the process a little bit easier. But I want to show you, if we have, I think I had it previously. All right, so here we've got our linear function, and I'm just going to increase the x values power by 2. So this is x to the first. I'm going to make it then x to the third, and then x to the fifth, and x to the seventh. Do you see some similar relationships here? Do you see, if I put the point 0, 0 on here, 1, 1, negative 1, negative 1, are those points on each of these odd power functions? Does that make sense? Okay, very similar relationships, right? The only thing that's happening is kind of in like that box. Our curve is snugging up against the x-axis a little bit more each time we raise that power, right? Okay. And it's the idea of taking like negative 1/2 and raising the third, it becomes negative 1/8, right? Okay, instead of maybe negative 1/4. So that's why for negative 1/2, this is snugging up against the x-axis a little bit more. We see those relationships. Is that okay, everybody? Let's look at taking this n value starting in at 2. Now this point here would not be negative 1, 1. It would be with negative 1, 1. And now we see, as we increase, okay, it's a very similar type structure, right? Except for near 0, 0, between negative 1 and 1, that thing bottoms out a little bit more. And it also gets, as we go on, beyond 1, okay, now I'm taking, like in this case, I'm taking 2 and squaring it. Well, that gives me 4. But here I'm taking 2 and raising it to the 4th power, so it increases to 16 so much quicker, right? Okay, well, if I go, 2 to the 12th, okay, I'm all the way up there. I don't even know what 2 times 12, or 2 times 2 12 times is, but it's giving me a very, very large y value very, very fast in regards to what x values I'm using. But the overall structure is similar, right? Would you agree that they're all kind of almost parabolic? Now, we don't call those parabolas. Only x squared do we call a parabola, but very similar relationships, okay? So that might help us as we start to work with some of the piecewise functions here in a little bit. There are some other functions that you guys are maybe familiar with that are going to pop up. We've got our root functions, okay? So with root functions, there's a very similar relationship to root functions as there was talking about the power functions. And the reason is that root functions are inverses of the power functions, okay? And we'll talk about this later on. I think it's the last section of the chapter. We'll talk about how we know what the inverse of x squared is, or what the inverse of x cubed is, and then the relationship that exists with the graphs. But the idea is, if I were to look at x squared and take the ordered pairs, 0, 0, and x squared, and I flip the x and y, I then get an ordered pair on the square root of x. Okay, so 0, 0 flipped gives you 0, 0. Pretty trivial, pretty basic. Take 1, 1 off of x squared, flip it. On this function, then you get 1, 1. Again, pretty trivial. The next ordered pair on x squared was 2, 4, right? Flip it. You get 4, 2. And that should make sense. If I plug x in right there, of 4, don't I get 2 back? Next one you probably try would be 9, 3, right? Okay, now the reason we're not trying the negative ordered pairs from x squared, like negative 1 or negative 2, is because when I plug negative 1 into x in this root function, what do I get? What's the square root of negative 1? I. And you can't graph that in the xy plane. Okay, so that's why we're only seeing kind of one branch here of our parabola. If you think about it, this looks very parabolic, and what we're missing to get the parabola would be that part there. Okay, but for a square root, that is undefined. Those values do not get used. Okay, so the cubic here relates to the cube root. So we had 0, 0 on the cubic, So flip the 0, 0, and you get what's on the cube root. We had 1, 1. Flip them, we get 1, 1. We had negative 1, negative 1. Flip them, you get negative 1, negative 1. So you see how knowing points off the cubic gives me points off the cube root, right? The other ones that were kind of unique were 2, 8. But if you flip those, you get 8, 2. And this would be negative 8, negative 2. Is that all right? Do you see then that x, I'm going to write it this way, it's just easier to say. We know the fourth root of x is the same as x raised to the 1/4 power, right? Is x to the 1/4 really the same as the square root of x, graphically? Looks very similar, right? Is x to the 1/5 very similar to the fifth, or the cube root of x, or x to the 1/3? Okay, so if we see, should be able to do this, instead of writing this as x to the n, let's write it as x to the 1/n, and that should give me the square roots, or I guess not square, so there's a square root, gives me the even roots, but are they all very similar? Do they all have 0, 0, and 1, 1 on them? Does that make sense to everybody? So all your even roots look very similar. Okay. Now for my odd roots, so let's start this thing at 1. Now obviously can't do that, can't divide by 0 here, so I don't know what's going on here, but you can't do that. But if x is raised to the 1/2, so that's the square root. I wanted the odd ones. Why didn't it give me this? Start at 1. Go to 19. All right, so we get, obviously x raised to the 1/1 is just a linear function, but then when I make this 1/3, there's my cube root, and then negative 1 will be on there. And then 5th root, 7th root, 9th root, 11th root. They're all very similar, right? Do they all have those 3 key points on them? All right, and committing that to memory and understanding basically how we deal with multiplying negative 1 and positive 1, or raising those values to exponents should help us retain those 3 points. The next series of graphs are referred to as our reciprocal functions. These are reciprocal functions here. Don't write those down. You don't need to know that stuff right now. We're not going to deal too much with reciprocal functions until chapter 4. Okay? Sometimes they're called rational functions because we're dividing by a variable term. All right? The last two, absolute value function. Now this is, I think this is kind of misleading sometimes. This is the absolute value of a linear, I'm just going to say input here, but that's linear, right? Okay, so what the absolute value function does is it takes your y values that are negative and it makes them positive, right? Okay, well then it doesn't just have to be a linear function that we do that with. We can do that with any function that we want to. Okay, so I'll just demonstrate this with, so I'm going to write f of x is equal to, let's just go with a linear function here, 2x plus 1. And if I go absolute value of that function then, it gives me that. Do you see how, if I start with the blue one, to get the red one, everything that's positive stays positive, right? You see how all of these values down here that the y was negative, that y value up here becomes positive. Does that make sense to everybody? Okay. So the idea is really, if you look at that graph right there, if you were to visually fold on that line, fold on the x-axis, and see where the bottom half plane, the third and fourth quadrants, where those points land in the top half plane, you are dealing then with what would be the absolute value function. Does that make sense? Okay. Now, this doesn't have to be linear. This could be, something like this. Okay, now here's the idea. Now think about this. Are all your y values there positive? So when I take the absolute value, are they still just all positive? And we don't really see anything different there, right? Let's do this. Let's say -1 now. If it's minus, now you got some y values that are negative, right? So if I take the x-axis and I fold on the x-axis, this little portion should go up here, right? And it makes that the absolute value of now a quadratic input. Okay? You can put anything in here you want. Okay, let's put a cubic in here. So there's my cubic. So now fold on the x-axis. Everything that's below the x-axis is going to get reflected up top. And now you get that orange or red curve there. Kind of makes sense what the absolute value does? All right, and it's important to understand this because they introduce it, and I think maybe a misleading way. They introduce it with just lines as your input, okay? But then eventually they'll just straight jump to using quadratics and not have a discussion of what's really going on there, okay? The next one is what we call a greatest integer function. This is probably something you guys have never seen before. But you are actually impacted by it. You guys all have cell phones? You got data plans? Anybody not have an unlimited data plan? Okay, so if you have a limited data plan, you only get like 10 gigabytes a month, right? Something like that. Let's just for a nice whole number to use. Let's say I have 10 gigabytes a month. If I go to and use 10.1 gigabytes, I get charged a fee, right? Is that fee the same regardless of how much more I use up until the 11th gigabyte? So if I use 10.1 gigabytes, is that the same fee that I pay if I use 10.9 gigabytes? Yeah. Okay. What that means to me is that Verizon or Sprint, whoever your carrier is using a greatest or least integer function to charge you. And here's the reason why. Think about this. One, that it's very lucrative to them, okay, because they're no matter how much of their data, because they're providing you a consumable resource, right? Consumable good. So this is the idea that, no matter what portion of that I use, I have to pay the whole price. Instead of prorating it, saying, I only use 1/10 of a gigabyte, so only charge me 1/10 of the fee. They're saying as long as you get into that next gigabyte, you're paying the whole fee regardless. Does that make sense? Okay. If you've ever made like a long distance phone call, or Chuck, you call psychics? No? Okay. You know what the psychic would probably say? Probably not going to choke on his bagel, but probably say you'd probably be more successful if you wrote notes. Huh? No? Okay. But if you look at like long distance phone calls or just like 800 phone calls when you call somebody like that, I use psychics just because people I think are familiar with that. But it says like for the first 10 minutes, this is the flat fee that you're going to pay. But then every minute after that, we're going to charge you maybe 99 cents or $1.99. And if you hang up before your first extra minute elapses, you're still paying 99 cents for that extra minute. Does that make sense? Okay. So you're going to pay the fee regardless of the portion of that extra portion of the good that you're using. That's a greatest integer function. Okay. What's the greatest integer? The way we evaluate this. So this is probably something different for you. What it means is that, and I think the naming of it is a little bit maybe misleading. Okay. But the greatest integer function, also referred to as a floor function. I like the fact that we can use the word floor function because what's going to happen is that you are going to round down. You're always going to round down to the last greatest integer. Okay? So kind of explain this with here's some different notation. You can use, so that symbol right there is a square bracket, and they add that little, I don't know what you call that, a little vertical line there to differentiate. But you also see sometimes the greatest integer function written this way. Okay, I like that because that little portion right there looks like a floor to me. Okay, or is indicating the floor, and it's basically telling me round down. Okay, if it was like this, what do you think that would tell me to do? Round up, right? Does that make sense? And if I'm rounding up, if this was the floor, what do you think this is going to be called? Ceiling. Okay, so we have floor functions, ceiling functions. They tell you to round down or round up. What the greatest integer function or the floor function, just using those as an example here, says if your input is anything fractional, okay, you always round down to the last greatest integer. So if 0.8 is my input, what is the integer on the number line, the first integer on the number line to the left of 0.8? Be 0, wouldn't it? Okay. You see over here, like at 0.8, we've got 0 graph as a y value. If I try f of 0.2, round down to the last integer, still 0, isn't it? So at 0.2, I get 0. If I go f of 0.99999, as many 9s as I can put on there, maybe I just repeat it. What's the last integer that I passed through when I'm at 0.99999? The previous integer would have been 0. See how we got an open dot there? Really close to 1, right? Now, the one thing we got to pay attention to is that when I put an integer in, when my integer or my input is an integer, the output is that integer. So I plug 1 in, I get 1 back. And that's why at 1, 1, we have that closed dot. But now if I go f of 1.5, the last integer I came across would have been 1. So at 1.5, we're at 1. Does that make sense to everybody? Okay. So the idea then is, let's say that my phone is free. I get no charge on my gigabytes from 0 to 1 gigabyte. But after I use 1 gigabyte, maybe I'm charging extra fee of, in this case, maybe $1. Okay, and then everywhere from 1 gigabyte to 1.9999999 gigabytes, I'm paying that extra $1. But once I hit 2 gigabytes, now I'm going to pay an extra $1 on top of that. Does that make sense? Okay, so that's the idea of a floor function. Now, the reason why we're using this terminology, greatest integer, think about this. If I'm going to plug in f of, let's say, -1/2, okay, -1/2, you're always going to and it's kind of weird thinking about this. I think using a rounding idea, I always visualize, especially with negative numbers, visualize a number line, okay? And if I'm on my number line, there's 0, there's -1, and I'm now right here at -1/2, instead of rounding down, I always make the argument, I'm rounding left. I'm going to the left, the next integer to the left. Does that make sense? Because now at -1/2, you see how I'm at a y value of -1 now? Okay? I think that's just an easier way to think about things. Now, if this was a ceiling function, guys, basically all that really happens is the closed dot and open dots kind of switch spots. Okay? And we can do transformation. We can move that thing up and down. We can stretch it. And we'll do those things later in the chapter. But that's the greatest integer function. So if you see that notation, that's what they're inferring. All right, so that, guys, is just, hopefully, a lot of that was review. Okay? I'm hoping the root functions, the absolute value functions, the power functions, and the linear functions, that's all Algebra 2 review. But the review aspect of things is so that we can all discuss a piecewise function easily. Okay, so this is where, if you haven't been taking notes, this is where it's really going to kick in. These are where, in the past, guys, and I don't know the reason for this, but people struggle with piecewise functions. Okay, so the piecewise defined function, ultimately what it is a function, so pass the vertical line test, but for different sections of the domains, we have different rules, meaning we have different formulas for different parts of the domain. So along the x-axis, okay, maybe between two x values, you graph x squared. But between another set of two x values, maybe you graph x cubed. And between another two set of x values, maybe you graph x plus 1. Okay? So instead of having just one graph, one rule that dictates what your y values are, now you're going to have several rules that dictate what your y values are. But those rules are determined by certain domain values. Okay? Because of that nature, we're going to graph it in separate pieces, and that's where we get the idea of the name piecewise. Okay? When you're done with this, you're going to recognize you got multiple pieces of graphs. So what I want to do is just give you the overall structure that these things look like. You're going to have some function f of x equals, now this is the way that they're written. Okay, we use this big curly brace, and then we start taking our rules. We might have a rule number 1. We might have a rule number 2. All the way down to rule, say, number n. And for each one of these, you will have a domain determined. I'll just say domain for rule 1. This will have a domain for rule 2. You'll have a domain for all your rules. Okay, and those rules will be algebraic. So they might be like x squared. There might be x plus 1. There might be x squared plus 5. They might be the square root of x. They might be the absolute value of x plus 3 or something like that. Whatever any algebraic function that we've talked about in the last 3 years can show up as a rule. Okay, your domains will show up in 2 ways. They will use inequality symbols. So they might say like domain for R1 there might be something, just give an example, they might say x is less than or equal to 1. Okay? They might say here that this rule is -3 less than or equal to x, less than or equal to 0. Here they might say that my domain is -7 to -3, not including -3. So you can see, I try to deliberately give you different ways that you might see the domain there. You might see that as an open interval. X is less than or equal, and that's an open interval from 1 to -infinity, right? Okay, and that's in set builder notation. It's actually using inequality symbols. Okay, rule number 2 is a closed interval. So we're going to include -3, include 0, and we're just going to look at the x values between those. And that last one is an open interval again, because we do not include -3, but that's an interval notation, right? So you might see them jump back and forth between the notation on how to express what x values you're using. Okay? So the first one I want to do here is very simple in regards to its structure and in regards to the rules. Different authors have different kind of preferences. You might see the word if here, and I like this. I like the word if, because if we parallel this to geometry, we have if x is less than or equal to 1, then you use x squared. Okay? This says if x is greater than 1, then use 2x plus 1. Does that make sense, everybody? So it's written as an if-then statement. I think that makes sense if we understood what conditional statements were in geometry. And they often, wrong button. They will often use that statement that they'll call this domain a condition. Okay, they might call that a condition. Does that make sense? Might call it a restriction as well. All right, this is how we do it. It's pretty easy. All right, now, there are some places here where you can get into trouble if you're not paying attention to the procedure, okay? First thing you do, you just choose one of your rules, okay? I always start top one and then work my way down. I mean, that's the safest thing to do. I'm just going to start with that and focus only on working with that one. Don't even worry about the other one, okay? First thing you're going to do is realize whether your function is linear or nonlinear. And what that does is it tells me how many points I need to graph for that thing. If it's nonlinear, I need more than 2. Does that make sense? If it was linear, you only need 2 points, correct? Okay. But if it's nonlinear, I need a series of points. I'm not saying I need 3. I'm not saying I need 4. I might need at some point 4. I might need some point 7. It just depends on which ones I choose. Does that make sense? And I think it makes sense for us to go back to those parent functions I showed you, and we have the, if I see x squared, well, now I know a series of at least 5 points that I can use, okay? Now, I know it's nonlinear, so I'm going to use multiple points, okay? I'm going to look at my domain rule. It says x is less than or equal to 1. I have to use that one, okay? And that's not because this is equal to, okay, because you're going to see down here in this bottom one that I have to use 1 as well. Whatever these endpoints are in our domains, you have to use those in your rule. So what I mean by using, I'm going to take that as an input value, and I'm going to evaluate. So if I plug in x to be 1, what do I get with that rule? If x is 1, I get 1 back, right? Now, because that is less than or equal to, I'm going to close that dot in. Right? And now here's the nice thing about knowing what your graph looks like. If you know what x squared looks like, you should be able to graph the rest of this pretty quickly from that point to the left. Okay? From that point to the left, do we know that 0, 0 should be on that graph? Do we know that negative 1, 1 should be on that graph? Do we know that negative 2, 4 should be on that graph? That kind of makes sense? Negative 3, 9, negative 4, 16. But once you get, and that should have actually been enough. But putting, the more points that we use, the better our graph will be. That's what that green rule that I highlighted is going to produce me. Notice we chopped off part of our parent function x squared, right? Okay. Our entire parent function x squared would kind of look like that, right? But we chop it off for values that are, we're only interested for values that are less than 1. Now that I've got that down, I'm going to go down here to rule number 2. And now it says, no matter what I do, I first have to use that as an input. Okay, so I take that 1, and I put it into my rule 2x plus 1. What do you get back when you put that into 2x plus 1? You get 3. Now think about this. Did I really plug 1 in, or should I really be plugging 1 in? Or should I be plugging 1.0000000000000 as many times as I can say that, and then a 1 after that, right? That's what I should be using. But think about this. If you do that, you plug in 1 point, an infinite number of zeros, and a 1, and you plug that in and you double it. You get 2 point, infinite number of zeros, and a 2. That's still pretty close to 2. And then you're going to take that number and you're going to add 1 to it. You get 3 point, infinite number of zeros, and a 2. That's still pretty close to 3, though? That make sense? So the idea is, if you plug in a number bigger than 1, the first number bigger than 1, you're going to get something back as a y value that is pretty much the same as what you would get if you plugged in 1 itself. It's easier to plug in 1 itself. So plug 1 in, and we get 3 back, right? Now, theoretically, I'm really not plugging 1 in. I'm plugging a number to the right of 1 in. And I'm not getting 3 back. I'm getting a number just above 3 back. So does it make sense why I have to have an open dot there? Okay. Now, 2x plus 1. What type of function is that? Linear or nonlinear? Linear. So how many points do I need to graph a line? 2. I've got 1. Okay. I need 1 more. So maybe I go to an x value of 2. Because that's in that domain, right? Does that make sense to everybody? Got to choose values that are in that domain. Plug 2 in, you get 5 back, right? And that's our piecewise function. The one thing you have to pay attention to, and this is something that I neglect when I'm just graphing normal functions, I forget to do this, is I got to put arrows on there. If I don't put arrows on there, you're telling me that your graph stopped and your domain would have been different than x is bigger than 1, right? If I want to put an arrow on there, maybe visually I'm inferring that my domain should have stopped at like 2.2 or something like that. Okay? You have to have those arrows if you need them or not. Open dots, pay attention to, all that kind of stuff. Now here's the idea. Is this thing still a function? Yeah. Okay. I passed there, right? The only real issue might be right here, correct? But how many times does that green line intersect the curve? Once. At the red dot, right? At the blue dot, we're really not touching it. We're just as close as we possibly can get to it. That's how we graph piecewise functions. Okay? Yeah. The last class got to this, so we'll start with this tomorrow. But if you get to your homework tonight, you want to work on it a little bit tonight. This is a rule. Okay, now it's got 3 parts, right? You can have as many parts as you want. But this is just asking us to evaluate g at -7. So I got to look at negative, that's an input, right? I got to look and see which of these intervals does -7 belong to. Does it belong to the blue one, the pink one, or the green one? -7 should be in the blue one, right? So I'm going to plug -7 into the blue rule. Okay? If I look at 16, where does 16 belong? Blue, pink, or green? Green. So I plug 16 into this to get my output. Does that make sense to everybody? Okay? So these tell you, okay, if you have in your evaluating process, you have a value in those domains that tells you what rule to use. There is an assignment open, not due for a couple days. We'll pick up with this tomorrow.